I think I'll start the class, and if you have any doubts, you can raise the doubts in the Tuesday class. And today's class, it's more of how to say it. It's more of like about the application of what we can use, and further we will see how can we apply these tools. I mean, whatever we studied till now, and how can we apply. In the last class, we have seen two examples, and I have talked about the MD simulation. And in this class, we will see some basic theory about the MD simulation and where we can do that. I think in this today class we will do that. So for that, one second. So I think my screen is visible. So what we are going to do was, so this is like extra class. So in which until week 11, what we discussed was like in the statistical thermodynamics. So first 5 to 10 minutes I will explain the what is the previous concept we had discussed, and then we will go to the new concept such that it will be like refreshing that okay, these are the things we have discussed. And initially we started with uh, the micro states and macro states. And here we have seen the combinations, like how many molecules can fit in this energy levels and all this thing, and energy level. So here we have come with the formula of sigma of ei ni, and n equal to sigma ni, and then we have started the w, which is nothing but thermodynamic probability. So we said that it's nothing but how the molecule stays in each microstate. And then from here we said that from the Boltzmann constant and all the things, then we have developed the probability function. So probability of ith state occurring is nothing but e to the power minus sigma beta I divided by into e to the power minus beta I. So this is the initially we started, and then we found out this is using a Stirling operation and Maxwell Boltzmann constants and all the things, and these things, and Boltzmann Planck postulates, where we are saying that S equal to K ln W. So after all these findings, we have come to the equation of Ni equals to N into e to the power minus epsilon I divided by kBt divided by so after solving the alpha and say if you remember, we have done this formula. I think x on x minus x, yes. And so and then we have the Boltzmann Planck postulates, and then we have all the formulas, and then we have come to this where ui equal to energy of the ith particle in the ith state, molecules having energy. So once we have discussed all these properties, then we started to figure out how to derive the U, G, and Gibbs energy, Helmholtz energy, pressure, and everything. And then at the end, we found out that as extensive properties, V is converting to 2V, N is converting to 2N, but S is not converting to 2S. So then you understood that okay, we are making some mistakes in the considering the micro states with macro states. Macro states with macro states. One second. So we have made a confusion with the macrostates with the microstates. So we are taking the what is the mistakes in this initially was we are taking the particles as distinguishable particles. So if you are taking consider the distinguished particles, say suppose it's like 1 and 2. So then what is happening was we are getting the more number of microstates compared to indistinguishable particles. Okay, so then we have followed the new I think then we have done again all the things and we found out that W equals to n factorial by GLNL divided by pi NL factorial. N is nothing but a degeneracy level. So after this we found out that S is equal to S. So this is the basics, and this all is nothing but a quantum state mechanics of thermodynamics. So then we came to the ensemble approach, because then we came to from quantum to ensemble. So what in the quantum the limitations are? In the quantum mechanics, the basic limitations which we have considered was the particles are indistinguishable, and they won't interact with each other. But in reality, these two are not the case. So then we have converted to the ensemble approach. In the ensemble, as we already discussed in the last class. So if you take this is the main ensemble. So suppose if you have a system of 2 microstates, if you have a system of 3 microstates, and if you have a system of 10 to the power 6, 10 to the power 12, and 10 to the power 8, the more number of the microstates is the better representation of the system. So that's what we understood in the ensemble also. So from here, if I take the definition, collection of systems which are macroscopically same but differ in microstates. So why I'm starting, sorry, differ in microstates. So why I'm starting again from the starting was to come to this line again. So we are discussing that ensemble is nothing but, so even ensemble, just assume that there are in that way there are n ensembles, sorry, n microstates. I can write it like n micro. Sorry, there is only one ensemble. I made the mistake. So assume we have ensemble with n microstates. So the macrostate of the n particles will be always same. So what does it mean? We have only 5 molecules under 100 degrees Celsius, under 1 bar, or under XYZ volume. Okay, if you consider any, if you take any random kth microstate, so belongs to n microstates, it gives the k equals to k plus 1 for all m macrostates, for all macrostates. So this is what I'm saying. But if you come internally, there is a difference. So if you remember the last class, we discussed the differences in R comma P, and then uh, we have gone through the ensemble approaches, and we found out that at the end we the interactions we have to considering the interactions. So we have the Q term. If you remember, so ensemble approach Q equals to integration of so then we can write this as P as e power minus h of r comma n divided by kt divided by q. Now here the q will be integration of drn dpn e power minus h r comma n whole power to the kt. So now this term is nothing but considered to the energy one, this one. So now we know that energy consists of kinetic energy and potential energy. For kinetic energy, we got p square by 2m. For potential energy of particular particle, initially we thought that if you have the system, the molecules will have the surroundings interaction. So that's what u of r plus the two molecule interaction. So then it will be of sigma u of ij comma r plus there will be three molecule interaction, like one comes and binds with the 2 and 2 comes and binds with the 3. So that's when u I j k of r plus and so on. But in general terms we have taken only the first two, u of r plus u of r. So after this this is called as effect of surface effect. Where the molecule can go and interact with the surface, where it collides with the surface, and this is nothing but the pair potential. So scientists have done many experiments to find out this pair potential. Which one was Hart's pair potential. And then if we come further, we have the square well potential. And then we have the soft sphere potential. So we have these three. The derivation of these three was discussed in the last class and even in the third class also. So these three, either they are focusing on either one of attraction or repulsion, but neither both. So then to discuss the short range, we have the LJ potential. So where it deals with 4 epsilon of sigma by r. So where this term indicates for the attraction, this term indicates for the repulsion of u of r. So basically if I keep this equation, so this is u of r and this is r. So if you have the molecule 1 here and the molecule 2 here, initially they are very far, so that it means that it doesn't have any attraction or repulsion force between these two. So that's why the value is getting near to 0. It's assume that this is a 0. Assume near to 0, and once the molecule starts moving nearer and nearer, it comes to a certain position where the sigma value will be more, the epsilon value will be more. This is the sigma. The sigma is nothing but this is sigma 1, this is sigma 2. So this is total sigma of ij. So once it comes to the very close, we have the attraction force between that, and that gives the attraction force here. So once it gets too close, there will be a repulsion force between these two. So that's what will be described by this. This is for the attraction force and this is for the repulsion force. So this is like, if you can see that, okay, when the atoms are very far, we are not considering that even they both are together, so the values are 0. So we are considering only when the molecules are very near a region. So that's why it is called as the short range interactions. Short range. So if you want to consider the long range interactions, then we need to go for the Coulombic interactions. So which is nothing but charge of the ith particle and jth particle divided by the dynamic diameter between these two. Diameter. So this is the one for the long range interactions. So to at the end, the final equation will be like ur bar, assume that this is bar, plus short range plus long range. This is between the two molecules, intermolecular interactions. So what about the molecules which are in the bond? Say, what about the intramolecular interactions? Say suppose you have the two molecules, and after some time these two molecules can be here, or it can be here, or it can be goes this side, or it can goes this side. Say suppose this is 1 2 1 2 2 1 2 2 1 1 2. So it can take any conformation, right? So if you see this all the diagrams, there is a distance. The basic difference is happening in this, the length between the, I mean the distance between the two things which were I'm not talking about the two molecules. If they are not attached, suppose if there are two molecules like this, we might have talked about the short range interactions because they are like they are not connected, so we can find the intermolecular distance. But these are two are the intramolecules, so as these two are the intramolecules, so here there is a difference in the bond. And what if I say that, okay, we have this type of molecules, 1 2 3 1 2 3 2 1 3 2 3. So if you see here, here the difference is in angle. So not only the short range and the long range of the intermolecular interactions, so we need to consider the interactions between these two atoms which are binding intramolecules, between the intermolecules. So that's why the final UR will be intra plus inter. So which is nothing but intra is for the bonds. We have the bonds, we have the angles, we have the dihedrals, and this is for the short range plus long range, plus we have the surface effect. So you know that as we discussed in the classes also, so it will be r minus r naught square plus theta minus theta naught square plus vn by 2. I'm not writing the sigma. So cos of nw plus minus omega, and plus long range and short range interaction. So now as of now we are not talking about surface effect. So how to omit the surface effect? Because see, why do we need to omit the surface effect was, if this is the box, we should understand that the energy exerted by every molecule will be same in overall system. So it is the energy exerted by this molecule is similar to the energy exerted by this molecule and the energy exerted by this molecule. So that's why the energy, if you calculate the potential energy will be constant. So at this time, say suppose if this molecule is interacting with this, these molecules are not interacting with the surface, right? So the term surface effect will have the huge impact on the total potential energy. So that's why we need to change the potential energy effect. So that's where comes the periodic boundary condition, further minimum image convention. This is all we discussed in the last class. minimum image, and then comes the radius cutoff. So what we are doing here was, so this is the box. So I have 5 molecules. So this is one box. I make parallel boxes in this. So what is happening was, say suppose in this effect, the molecules, if the molecule is go to this side, the molecule will come and join this side, or from the here, or from the here. If the molecule goes in any one direction, the another direction from the molecule comes and joins, and in that way we are calculating the interactions of all. Say suppose here, it's like if the molecule goes here, it means this molecule will come here, and this will come here, this will come here, this will come here, and the molecule will join here. Okay, so it means the number of molecules in the box are not even changing, but the basic how to say it, the basic disadvantage of the PVC condition is, the basic disadvantage, the basic disadvantage of the PVC condition, we are calculating the n number of values. Say suppose we are calculating for this molecule and this molecule, this molecule, this molecule, this molecule. It's like we are calculating n molecules for n times. I mean, how many dimensions we are considering in all three XY directions. Okay, so now what we can do was, instead of that, we bought the minimum image convention. So what it does was, suppose if you take any one molecule, say suppose I am considering this particular molecule, sorry, this molecule. What I will do was, I will keep the same. Suppose this box size is 4 into 4 into 4 angstrom cube, sorry, angstroms. So then what I will do was, I will shift the entire box considering this molecule as a center. Okay, so now what I am doing was, in that way I am omitting this molecule, and I am calculating the interaction between this this one, and this one, and this one, and this one, this one. It's like if I have 5 molecules, we are considering the interactions of like this. So which is nothing but n into n minus 1 by 2. Okay, I think this is concept. So even suppose, see, this is happening in the minimum image convention. If you do the PVC, you are doing this for in the one box. Okay, this is happening for the one box, and second box you are doing the same thing. The third box you are doing the same thing. So you are doing for n interaction with n molecules. So that's why the number will be more here. Yeah, the number will be more here compared to the minimum image convention. And further we have the radius cutoff. So what does the radius cutoff do was, okay, I have taken this as center, and now I will put on a radius cutoff such that, okay, in this molecule only I will consider the interactions of this particular molecule. So that will further reduce the number of interactions from n square, n into, sorry, not n square, from PBC to the radius cutoff. So this is, and then I have shown some examples. So we have discussed the examples of the how the drug will move out from the binding site. And another example was, we have taken the lipid bilayer and how the drug can permeate. So these are the two examples which I have done, and these examples, as I said, that to understand any algorithms, it's better to use Frankel and Smith book of molecular dynamics simulation. So I shown the images last time also. If I have the images, I can show it later again. Yeah, see, if you see these images, where we have discussed the drug binding affinity, like where the drug is moving out of the pocket, and then we discuss the parameters of this. And the second example, we have discussed that, okay, drug is kept away from the box, and then we started pulling the drug into the inside, so that to understand the effect of cholesterol on the drug. So I have now discussed the way how can we do this. Okay, this is like, suppose I can say randomly that, okay, I am moving it. So this all can be done in the software. So the software name is the basically the well known for the molecular simulation or anything was Gromax. So if you open, there is a Gromax tutorial. You can, if you just Google the Gromax tutorial, you will understand that, okay, what is a Gromax and all the things. So today I thought I will show you an example, not an example, not exactly kind of the example. I will explain you how the system is been can be generated with the example of water, and then how it can be run. So this is what I thought today I will explain. So I said that initially, okay, then we can discuss. Okay, yeah, I will discuss whatever the sir has discussed for few parts today, and then remaining parts I will discuss in the next class. Uh, Join the class. Fine, no issue. I think I will record the class. So just assume that you have the water. I said that okay, you have 100 water molecules. Say you have 100 water molecules. And given box size is, assume for 100 it might be around 1.5 nanometer cube. Then you can write, say, yeah, 1.5 nanometer cube. It means it's not 1.5 nanometer cube exactly. So you have box of, so now what does it say? So now we need to take a box of this dimension 1.5 into 1.5 into 1.5 in all the directions. So this is box. So assume that this is the box x, y, z directions and of 1.5, 1.5, 1.5. So now what we are doing is we are taking the box and we need to fill the water molecules inside the box. So now how can you fill it? Say suppose there are two methods to fill the water molecules. So there are two ways. Sorry. In different ways we can fill the water molecules. Say suppose this is the box and I am say suppose I just put the 100 molecules inside, so it can take random positions, no need to be in the linear position or anywhere. So it can take the random position, or we can put the exact positions. Like I say suppose I want to insert like this. So either we can do random in insert or specific. Okay, if you open once the Chromax tutorial, you understand what I'm talking. So, say suppose what I'm thought to explain was in this class, I thought to explain the basics of this class along with the algorithms which we use and how it will be useful in the simulation point of view. With the example of water, so suppose you have the water box 1.5, 1.5, 1.5, and you added the water. Say how to add the water into the box. So that is the first question we need to ask. So there are two ways to add the water. Either we can add through the random way, like just randomly say that okay, I am adding that 100 water molecules and just add it randomly. Otherwise you can add it in the like specific pattern way. So once you add it, so you added the molecules, and you know that density equal to mass by volume, and if you do the density calculation, uh, it means the m, suppose you know the density of water is 1000 kg per meter cube equal to m by v, which is x comma y. So what I want to say was, if you take certain molecules of m and then certain molecules of y, then only you will get this certain amount. So it means m means nothing but number of molecules and the volume is both are linked here. Say suppose you have given such a I'm just assuming that whatever the properties you have given, there are 100 molecules on the volume. If I use, assume that I got the, how to say it, hmm, density of, say, suppose volume is higher, so volume is higher means the value will be lower. So I got, just assume that 8 kg per meter, 800 molecules. So how can we make this value to 1000 kg per meter cube? So anyone knows how to increase the value? Okay, fine. So how can we do? So basically, if I'm given that, say, suppose, see, once you add the molecules, you can't increase or decrease the molecules because the molecules are constant. So I said that I want only for 100 molecules. I want to check what will be the density of the water. Yeah, density of the water. Say the molecules are constant. I'm not going to add more than 100. So now you need to play with the play with volume. Okay, now because volume we can change it, right? Because we need, with respect to the molecule, the volume will change. So now the density is 1000 kg per meter cube is reduced to 800. It means you need to increase this value to 1000. So it means you need to, what you can do. So if you have the low value and you need to increase the value, so you need to have the lower volume. So you need to decrease the volume. So you will use the NPT ensemble. You understand why we are using NPT ensemble? Because we have different. So the ensemble is nothing but ensemble is nothing but we have number of macro states, same macro states with different micro states. So what we will do was we will maintain a overall macro states as same. So that's why either we can use NVT, NPT. Assume that you are using two. So we can't use NPVT. So you can say that, sir, why can't we use NPVT? Because we know that pressure and volume are both interlinked. So that's why. So once you add the molecules and if you kept it at the constant temperature of 300 degrees room temperature of 27 degrees Celsius, is another one is 300 Kelvin, and number of molecule as 100 and pressure as 1 bar. After some time you will get the value as density as 1000 kg per meter cube, where the volume from initially from 1.5 nanometer into 1.5 nanometer, it might be reduced to 1.32 nanometer or somewhere, like in this way it may reduce, it will reduce. Okay, so now to get the desired properties of density, we are doing in this way. Okay, this is the one classical example of how we can use the Gromax. And okay, first we have this Gromax. So how to get the different ensembles? So this is the first question: how to get the different ensembles? Yeah. Before that, I want to say one more thing. Say suppose uh, first you are adding insert molecules and you are adding randomly. Say suppose the random will go like this. So first it will take all the free space. So now once the free space is done, there is still space, right? So suppose there is still space, right? So now the molecule goes and sits here. The molecule goes and sits here. Okay, like this. If the molecules are going too close together, it means there is a higher energy, because if the molecules two are so much nearer, it means the initial itself we have higher LJ potential values. Okay, so to omit this, we will do the energy minimization, where we will make the molecules to kept at certain distance. So how can we attain this was, say suppose we have molecule at the position kth position, I will show it in the code wise also how we are running it in the system. So kth position of X molecule. Now what we will do was we will change this position of X such that X plus 1 should be. So this is the equation. So this is the oldest position, and alpha, and this is the gradient descent, and this is the convergence. So based upon this formula, suppose I have this molecule. See, gradient descent means you are decreasing. So that's why decay will always be negative. So what you are doing was you are moving this molecule here, and then you are calculating it how much the what do you call the energy will be. If the energy is low compared to the previous step of second step is lower than the first step, then we will process until we get the desired value. So in this way we are keeping the molecules at certain distance such that the value of the potential energy will be minimum from the starting. Otherwise, if you see, if you take this conformation itself, the LJ potential values will be higher, which gives the total potential energy or total energy in much higher rate. So that's why what we are doing was we are doing the energy limit such that the molecules will be settled down in certain places such that it's assume that it's like in a one room you have 10 chairs and you are all sitting together, okay, as a group. So then somebody comes and asks that, okay, you can go and sit in the different places to occupy the room such that it will be better to look and it will be better to interact with all of the together. So assume that it's the same case. To reduce the higher potential initially, we have carried out the energy minimization, and the algorithm which I explained, the x k plus 1 position is nothing but x k plus alpha dk is nothing but the steepest descent, where we are descending from the first initial step to the second initial step. So this is the steepest descent. So on every step we are calculating the potential energy with the bonds and all the things. So once we got the graph of potential energy like this, at some point of time we will stop. So once we got this constant value, we say that, okay, the value initially is constant, so then we will start the experiment. So now once we have the values, okay, now we are running, say, NPT. Okay, how does you will go from, as I said that as I discussed a long back, ensemble is nothing but different macro states, right? So suppose I'm just giving 1, 2, 3 and n. Ensemble, what does ensemble define? Is same macro state with different micro states. Okay, so it means if we have 5 molecules like this, in the next step the 5 molecules will be like this, in the next step the 5 molecules will be like this, and then in the end the 5 molecules will be like this. So now so this is simulation, right? So as time progresses we are saying that we are getting the new conformations. So but how can we get the new conformations? Like how can we move from r of t to r of t plus 1? So r of is nothing but the coordinates, the direction. How can position, not the direction also, it's more of position. So how can we go from one position to another position? That's where there are different assumptions and all this, so we will go from one by one. So this is basically of so first I explained we have the system, and then how to make the system. So this part is covered. So this part can be done by random or specific insertion. So once you have done the random or specific insertion, we know that the value of potential will be higher in the initial case because the two molecules will be nearer. So then we are running energy minimization. Okay. Now after energy minimization, the first question comes was into the mind was, okay, before energy minimization we have the force field parameters. So once you have the system, we need to know the force field parameters. I will explain these force field parameters also. Okay, once we have done the energy minimization, we want to get the new NPT, where we will get the new conformations. How? Where we get new conformations. But how? So this is the question. So we know that the basic equation of Fa is Ma, and this is nothing but, if I am making in terms of total energy and sorry, so you know that force is nothing but the change in the potential energy with respect to the position. So it's like displacement time. So now we have this equation. So what does it says was, we are getting the changes in the r with respect to in the file of u of r. So how we will get it? So to derive it mathematically, we are using the two first order. We are converting these equations into two first order equations. So what we basically how we can write A as d square by dt square was, velocity is equal to dr by dt and A is equal to dv by dt. So it's like a d by dt of dr by dt. So it's nothing but d square r by dt square. That's why we are written here as this. So now we are considering this equation. We are breaking this equation into two order equation. So the first equation is A is equal to dv by dt, and we are integrating now dv equal to A into dt. So now dv equals to integration of A into dt at from v0 to vt at from 0 to t. So now we get vt minus v0 equals to A into t. So vt equals to at plus v0. So this is the first equation. So now the second equation is v equal to dr by dt. Now dr equal to v into dt. So integration of r0 to rt. Rt is nothing but at time t equal to 0 and time t equal to t. That's what rt is nothing but at time t, what is the position? R equals to, so time 0 to t v dt. So v from 1 we have r0 rt of dr equals to 0 to t. So this is vt dt, sorry, v0 dt plus at dt. So you can see this equation, this v same, and so that's why we get it. So if I express this equation, I get v0 t plus of at square. So now rt equal to v0 plus, sorry, r0. This is r, right? Not confused. So this is the equation, but how we will get see what does this equation says was, we need to know. So this is the main equation. So based upon this, many scientists has developed algorithms which is known as integration algorithms. As this will take so much time, so now to define velocities of initial, so we need to know the initial velocities, because we can know at r equal to 0 what is the position from the whenever you draw the system. We have different softwares like Gauss View or OpenBabel, or if you draw any 3D structure, you will get the initial coordinates, and if you have the velocity, you can get the initial acceleration also. So now the term is how to get the velocity. Further, different scientists have developed different algorithms, and the algorithms are known as integration. So one of the few famous are Uh, Verlet, I think Verlet, yeah. So what are the basic assumptions they have taken? So to go from V max to V minus max minus V max, the two assumptions made was kinetic energy equal to half the total energy. The kinetic energy should always be equal to total energy, and then the total momentum should always be equals to 0. So these are the two assumptions which has taken to calculate the initial velocity, and by applying the probability condition at this condition we get probability of Vi of x, we get was so this is the probability equation which we will get. Now to understand the both velocities and this one, the scientist has developed formulas based upon the Taylor series. So I will explain some Taylor series. So now why we are doing this one was, I will explain it later again. So the few interesting ones are numerical algorithms where Verlet, leapfrog, velocity Verlet, and few other. So I will apply the, what do you call, I will take this equation A, and I will take this equation as B, and I will apply Taylor series on this. So if I apply Taylor series on B first, so then I will get, if I apply the Taylor series on the B part, so the changes in the time gives rise to, if you see the equation, it's like R naught, which is at t, plus V naught t is changing, so it's like V naught dt, that's the change time, and then we have of at square dt. So of a dt square. Okay, so now this is also like, if I want to write it in another term, it will be of R naught of t plus partial derivation of t of, so v of t plus half v of t dt square. So then I will write the same for v of t plus dt. So we know that this is nothing but, so we can increase this equation so on so forth. So the equation is v equal to v naught plus at, right? So I am writing off again. So now the equation which I have was v of t dt. So now plus and so on for dt square. So we have t dt square dt cube and so on so on. So now how can we get the r of t and v of t? So now first, if we take the velocity algorithm, what he has done was, he has taken r of t plus t, so it's nothing but r of t plus v naught dt plus, and he removed the extension terms, the higher terms. So then for the better understanding, so he has taken r naught of t minus v naught of dt plus, so he added the both. equals to so this equation will give rise to this is a partial derivative. So if you know the particular position, say suppose at fifth position, you know fifth second, you know the position. Maybe for sure you know the fourth second, then you know the sixth second position. But here it is not extensively calculating the velocity. So that's why we are many people are using the leapfrog algorithm. So many people uses leapfrog algorithm for the big systems, for the macromolecular systems or biomolecular systems. So what he does was, so he takes this way. So he's done the off dt. So what he does was, so because it is off dt, so off dt of t. So now he mixed both. So now what he did was he taken this formula, the leapfrog guy. So now r of t plus he has taken the dt common, so it has become as v of t plus of e of t dt. So which is nothing, this is nothing but this is going towards v of t plus of delta t, and we have already dt. So plus r naught of t, so it is equals to r of t plus delta t. So that's what this equation says. So what does this equation says was, it has mixed the correlation. So correlation of r of equals to so now what will be the value of v plus half dt? So for that, v of t plus of dt equals to v of t plus half dt of t. So v of t minus half dt equals to v of t minus half dt of t. So we need to cancel this. So we get t plus half dt minus v of t minus half dt equals to dt at. So if you know the acceleration, initial acceleration, so what does it do was, say suppose if I have kept 0 to n seconds, so then it is first second, this is second, this is third, so it means r0, r1, r2, r3. So then we are calculating v here and v here, sorry, v middle. See, because it is rt equal to 0, t equal to 1, it means r of t plus delta t, so it will be v of t plus half delta t. That's what we are calculating. So that's why the r will go in the direction of down, and it goes in the leap, like one another again. So that's why this is called as leapfrog algorithm, which is used in many cases of now. So using these formulas, as because the energy term, the calculation will be so expensive, so that's why we are getting the new coordinates using this equation. So if you take this question, so what we have done was, so initially we have talked about the system, then how to add molecules to the system, how how to add molecules to a system, and we also see that how to add either random way or specific way. Once you add the random way or specific way, if the two molecules are comes near to each other, then it has more potential energy. So to reduce the more potential energy, we are doing the energy minimization. Then to run the any ensemble, we need to calculate the new positions, like we need to get the different macro states, right? So different macro states with the different micro states. So there is a computational expensive, so that's why we are using the integration algorithm. So where the most frequent one is leapfrog algorithm. Okay, so this is all fine, but how can you define the molecule to the system? See the computer, to the computer. So after this, you will get. Suppose if you are using NPT, it means at the constant temperature and pressure you are running the system. So obviously this will go. Suppose if it is 1.5, 1.5, 1.5, this will come as 1.32, 1.32, 1.32. Yeah. So yeah, this is all like how can we run the system, but how to define the system. So that is the next question we need to ask by ourselves. So how can we define the system? So to define the system to the computer, we need to know the parameters. For these parameters, there are different softwares to get it. So one is Amber, OPLS, there is Charm. Based upon the system and the feasibility of that particular parameter, to that we can apply. So what does this parameter says was, say suppose see the bond between C and C is always constant, O and H is constant. So this all bonds are constant, right? So that's why we are predefining the values of this bond. So suppose if there is a bond of, say if the molecule is like this, I can keep it like this, that is far better. So this is the example I'm taking. I'm just writing the example. So I'm naming it from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now we have the we need to write. We have okay. I have XYZ coordinates of 10 systems, 11 systems. So this will be non-filling another non-bounded parameter. So we have, if you see, we need to have the sigma and the epsilon values to calculate the LJ potential. So that values will be given, what is the value of sigma for carbon and what is the value of epsilon. Yeah, sigma and epsilon. So these two values will be given, and then further, suppose if we come, we can write like this. So the computer will take in the mathematical form, the digits form. So what it will give us? So there is a bond between 2, 3, 1. 1 is nothing but the harmonic, which constant you need to use. So suppose in the formula we have k by 2 r minus r naught whole square, right? So for the k we are giving this one, for this term, which one to use. So if you are using 2, 3, 1 and the value x, y, z, x, y, sorry x, we will give only x. So I am taking the example of, different color. So this bond, only the hydrogen carbon. So we know that the second carbon is binding with the third hydrogen, and I need to take the harmonic constant and the initial. So it will be like the first atom, the second atom, and which potential to use, which potential force, and the R naught value. So R naught value will be suppose x, y, z. And what you will do was, say suppose if you are running the simulation as using the algorithm formula, and the molecule has moved somewhat far and the potential energy has changed. So how you will calculate the potential energy change of that particular system was, you will do bond plus angle plus dihedral plus short range plus long range, sum of all these things. So there you will see that suppose if this bond is, instead of this it will go like this. So it's, suppose if it is 0.8, it went to 1.3. So now the value will be like you are using 1, so it will be k by 2 1.3 minus 0.8 whole square. So in this way the values will change. So this is the way to write. So suppose you want to write the angle between the 852. So you are talking about, if you want to talk about the angle between the 852, so you can write simply. This is for the bonds. You need to mention all the bonds together. So if you mention 2 comma 3 or 3 comma 2 is same, because we are considering the periodic boundary conditions and minimum age in convention, and you don't need to mention 2 times. So then comes the angle. So where we need to write, okay, first one is 8, the center one will be the middle one, 5, 2, and then here will come this one, the potential force. So this is first atom, the second atom, the third atom, the potential force, and the theta naught value. So same thing, the potential force, suppose initially it is some angle 4.5, and then it is converted to 5.5. So we will have the formula of 5.5 minus 4.5 whole square, k by 2. So in the same way for dihedral and also, so these are the parameters. So now you all know, okay, if given a system, first how to generate the parameters. So once you have generated the parameters, now you need to put it in the box. So now after putting the box, you need to do the energy minimization. Once you have done the energy minimization, we will get the coordinates, and then you run the ensemble averages to get the desired properties. Okay, any doubts in this part? No one join the class. Okay, fine, no one join. So if you have any doubts, you can ask. Otherwise, I will show some examples regarding this. Say suppose, okay, I will show you the examples. So I think I will share you the screen. So I'll add this PPT also, the new one. One second, just Gromax workshop. So yeah, so this is one of the nice tutorial for the Gromax. So the basic steps in the Gromax are, first you need to install the Gromax, and then once you install the Gromax, you need to create the files. As I said that, okay, which files you need to generate. Suppose I want to see the interaction between the water and carbon dioxide. So you need to create the files of water and then carbon dioxide. So this. So first you need to install the Gromax. So after installation, so creating files in the sense, say suppose you want to see the interaction between, for small examples I can take H2O and CO2, or if you take a big systems like protein and drug, in the presence of water. So you need to prepare the system, so you need to draw the structures of this, or you need to hold the structures, and you need to put it in the box. Then parameter file, so you need to generate that to the system that, okay, these are the parameter files which we are taking, and you need to be careful that whether you are choosing the amber, charm or OPLS, because somebody has done, say suppose amber has calculated the properties in the soluble format, and the charm has calculated the format as through the experimental studies. So you need to consider through the literature which one will be better and which one is not. So based upon that, we can calculate the parameter file using charm or OPLS or amber. So once we done this, then we have the energy minimization, as we said that, to reduce the total energy, potential energy. So then we are running the ensemble, and why we are running different ensemble was, this is for the small systems under steady density and all these things, and this is to get the optimized density. And we can't run NPVT, because as we all know that the pressure and volume are two independent terms. They are not such two dependent terms, so that's why we can't keep both the constant. So then analyze the result. these are the basic steps which you need to follow. And once this is step done, so now you got all the files. So I will show the example. So for the so in the following slides I will explain you okay what will be there in the upcoming slides. So you need to understand, and once if you don't understand it, go through the video, and in the next class you may ask, then I will explain it again. So basically you can go through the gromax.org website, and there from there you can download it, and it can be operated using the Linux environment. And in the I think in the gromax website itself it has given the readme file how to download it. So this is the file downloaded from the readme file. So how to tar it and how to extract it, and then how to open the files and do the things. So once you download it and once you install once you download it once you download it and once you installed, and then we'll go to the file formats, the creating files. So as I said that okay, I have the files of pdb. You can see it here. I think so if you see here, you have the water molecule. So we need to consider only one molecule. That's why if you see, we are mentioning the water as sol, in the terms of solute, sol, and here it says. So now if I give okay add H2O, so you will give the command like this 100. So it means it will go like this. So if it is the one compound, so the first compound is like this, right? So this is x1, y1, z1, x2, y2, z2, x3, y3, z3. So now if you are adding, say about 100 molecules, for now I am just keeping it as 5 molecules. So 2 molecules. So if I want to add the more molecules, so how does it add was? So it will add down to it. So but here the numbering will be changed. If you remember, so it will be x4, y4, z4. And so on for the 100th molecule. So it will be like how much? 99 molecules we have added. So each one has 3. 9 3s are 27. 27. So it will be 298, x 298, y 298, z 298, and so on. W sol HW2 300. Okay, so now in this way the molecules will be added. So you can add it either through Avogadro or Orca software or Gauss view or internet also. You can directly get it, and these are the information which you already know. So the distance between the energies on the hydrogens is 0.41 because this is a highly electronegative, and the distance between hydrogen bonding is 1.35. The least one is 3.14 hydrogen bonding. In the range of 1.5 to 2.5 it will be oscillate, and the angle between this 1.33, and the input files of the gromax file will be .pdb, .gro, .itp, and all these things. So So once we created the file, now we need to generate the parameter file. The parameter file in the gromax format is nothing but a topology file. So it has these properties. So here we define the defaults. So defaults means which will be common for all the system. One as the value and genpair no as it is default, and you can give yes and add pairs options here at the down. So here we are given, if you see, here we are given the sigma and epsilon values. So sigma and epsilon values, and the charge and the mass. So from here we can calculate the Coulombic interaction or the LJ potential. I think if you have any doubts, you can ask me in the next slide. So here we define the non-bounded values. So if you can see that we have written that here we define the non-bounded values for the calculation of LPG potential for only water. Further, if you plan to simulate, say suppose if you want to add the ethanol also, then you can add the CX, CY, CZ, 12.000, 12.000, 12.00, the charge of XYZ, ABC, W, XY. A type, A type, A. So this is the water, right? So this will be B type. So this is, type means which type of molecule. So this is one type of molecule, this is another type, right? So we need to write the new type, and this are the sigma epsilon values. So we need to add that in that such way the O values. You need to add in such a way that all the files should be in the together. Like how the topol file will consist of all the files. Sorry, how the grow file will consist of all the files together. In the same way, topology also. So in the atom types, it should be all together in the atom types. So once this is done, so now we are going for the ITP file. So you can see that the molecule type, here we define the type of molecule and non-bonded interaction exclusion. I mean, we are not excluding the, we are excluding the non-bonding interaction which are more than 2 atoms away. Then we have the atoms. So we can see that we are residing, this is a sol. So this is the molecule name of water. So we are putting name as solute. You can give any name. Either I can give my IIT also. So it all depends upon like. So the system doesn't care that whether you are giving the solution water or IIT or what are the names. So the name should be like in general. Suppose in the same there is a OT, HT and T, and then this is the names, which will be, if you see these names are in line with these names. Okay, these names. So you need to remember this. So this is for the system's understanding, because here we are making the, we don't want to repeat the statement. So suppose if you repeat this system, the system will store the memory as a OW, HW1 and HW2. Instead of that, we want to store the both information in HT itself. That's why we are keeping the same name. And then bond. So if you see here 1, 2, 3 number, if you see this numbering, so we have 1, 2 bonds. So 1, 2 bond is 1 and 2 bonds. So it is like OW, OH. So this length is given, see, length is given and the force constant is given. Force constant is nothing but K by 2, and the length is L0 is given. It's like 0.09, and if it is fluctuating, it will go more. So that's why I think it is here 0.09 is written. See, this value is here 0.09, and the same thing with the angles. And there is no dihedral between the water molecules in the intra-water molecules, so that's why we are not giving anything. And see, if you see it here, we have given the properties for the bonds, the angles, and for the LJ potential and Coulombic interaction. So then we calculate the potential and we calculate the integration algorithm and all that. So this is how the topology file is created. Hash include non-bonded. Non-bonded parameter is this file. So this is called as non-bonded, where it has no bonded interactions. I mean, this file deals with the only non-bonded interactions. So here, if you see, there is no bonded information, and if you see, this all has the bonded information. So that's why we are writing the two in different names. So this basically defines the non-bonded for the sake of our understanding. So this is for the bonded. So if you have any errors, it will show you which file it is. So it will be better for us to relocate and everything. And then system, I'm just having the water. You can change the name to, suppose, CO2 water. If you have the CO2 water, you have the protein biomolecular system, or if you have the RAG pathway, you can write the RAG pathway and all the things. And here we are adding the 500 molecules. So I given the experiment for the 500 molecules. So This way you can define the topology file. So if you see it here, in the initially we have discussed that once you have done the structure and then parameters and insertion, and then you need to do the energy minimization. So why we are doing the energy minimization was to determine the proper molecular arrangement, and that's what I said, right? So when you don't want two molecules to be together, so that it has the higher given force. Force is nothing but changing the potential energy with respect to the time, and we have the use of algorithms to find the global minimum. So that's why we are using this time, and this is the command which we'll use it in the Gromax. So these are the Gromax commands. So it's better. I mean, if you have a Linux environment and if you have a higher threads or a higher processor, if you have the cluster access is possible, try to run the Gromax. It will be easy and it will be better understanding of the thermodynamic properties. So if you see here, this is the steepest algorithm formula. Sorry. So where xk plus 1 equal to xk plus alpha k dk. So gradient descent, maybe you have heard the term gradient descent morely in the machine learning, where we have the system, the loss function. So it is gradient decreasing and then it is increasing, and then we will take the minimum path. So you're also doing the decay is doing the same thing, negative gradient. So it means it is going down. So it means it is going to the slope. So it means once it reaches the slope, then it reaches this. So it means it won't have this upper curve. Okay, so it will go up to only here. So now, so if you see here, this is one of the script file which we will use to run the simulation. So this file. So here you see we have the integrated strip to design the steepest descent, and we are giving the value as 1000. If the maximum force is 1000, then please stop it. So don't go further. So this is our stop function. Do not get further. And EM step. So EM step is nothing but optimal step size. So if you see that optimal step size, we have given the value of 0.01, which in line with this value. This is the value of that, and we are doing for the n steps of 50,000. So either it will run for 50,000 steps, or it will run till. So we are using two loops here. Either the system will run for 50,000 steps, or force equal to 1000 kilojoule per mole per nanometer. So whichever is the first, it will stop, and then it will goes to the stop. Okay, this is what happens here. And if you see the cutoff scheme varlet, so to define the buffer neighbor scheme, and then grid PME. So the PME is the one method to understand the how to say it, to calculate the potential mean electrostatic force. And then we are using, see, if you see R cutoff Coulomb type cutoff scheme, we are using varlet, and then R Coulomb, R VW. So VW van der Waal, how much should be taken, and R Coulomb, how much to be taken, and the PVC XYZ. So XYZ in the sense we are keeping the box in all directions. So what is the use of PVC in XYZ means? So suppose assume it like you have the big water scale, and if you explore XYZ of water, it will be all look like water only. Instead of that, say suppose you have lipid bilayer, you kept the lipid bilayer, not lipid bilayer, say you have taken the protein and you are keeping the two only in XY direction. It means the Z is simply nothing but the replica. You are not replicating. So if you are not replicating, whatever you are replicating in the 2D plane, the top plane and the down plane will be same. Okay, so it means it has more chances of getting the corrected result compared to the experimental result. So that's why it's up to us to understand that, okay, whether to go for all directions or like 2 directions or 3 directions. So yeah, this is done. And if you have any doubts, you can ask me. I mean, we have discussed like 3 parts. So in this class we have discussed so in this class we have discussed that, okay, how to take the system and how to insert the system, and then what are the parameters we can have to that system, and what are the parameters, non-bounded and bonded parameters, And then once we have the non-bounded and bounded parameters, so we are running energy minimization to understand that, sorry, here we are running energy minimization. Once we are running the energy minimization, we are running the ensemble averages, so then to our results. So this is the basic flow of how we can run the biomolecule system, so which I showed the example, biomolecule system. So if you have any doubts, you can ask me. And this way we have considered the force field also. We have discussed the parameters, so different parameters. The force field, we have considered the half of the last week class, the force field and integration algorithm. So then once you are running the energy animation, how to generate the new coordinates. So we have generated through the integration algorithm, which I showed there also. So then what else we discussed today? Yeah, so if you have any doubts in this class, you can ask me in the next class. If you have any doubts, you can ask me. So if no doubts, I think nobody is in the class. Thanks for attending the class, and thank you.